Hello guys, I guess we are live now. Let me check. Okay. Yeah, we are live. Hello everyone. Hi. How was the contest? I guess it was quite easy. How many solves you guys had? What code style? Maybe. Okay, so in division 2 also many people solved it. But let's see. Quality problem. So we are going to discuss up to E2. Okay. In this, which means we are directly jumping to E2. We will not discuss E1 because you can just copy paste the code in both of them. Yeah. So shall we start with the stream? F. No, not F, but till E2, 6 problems. I liked S F, but I didn't solve it in the contest. I was doing some work, so I just left the contest. Yeah, so I will try to solve it. This is the most difficult. No problem. And just look at it. Was more mathematics prone, I guess. A lot of mathematics was there in all the problems. I have to say. Okay, so let's start with the contest discussion now. Before that, I just want to let you know that we have also started the Instagram channel. You can follow us there also. And we have planned a lot of great things for you guys in the Instagram channel. And maybe we will be live on that platform. Okay, so you can just check best contest ever. So I hope you all get a positive data now. So let's start with the first problem, which is friendly numbers. It's a division 2 problem. For any integer x, we call another integer y friendly if the following condition holds. Y minus dy is equals to x. I have not solved this problem A or B of div 2 because I wasn't deep. So let's solve it together right now. Okay. So y minus dy equals to x, where dy is the sum of digits of y. For a given integer x, determine how many friendly numbers it has. Okay, so here y minus dy equals to x. Okay, yeah. So in the first problem you are given with you have y minus dy is equals to x, and this is digit sum, and you need to find all the valid y's, I guess. Okay, all valid y's. So to find all valid y's, what I can do, I can just switch this thing into here. So it will be y is equals to x plus dy. Now this is digit sum, and x is up to 1e9, right? So there are 9 digits at most 9, 10, 11. Let's take, we have some 15 digits. Y is up to 15. So I can take, there are 15 digits. It won't be more than this. Okay. So there are 15 digits. Now, if I have 15 digits, what is the maximum sum dy that I can have? 9 is equals to 0, count 10. Not sure. Look, what I am thinking right now is the maximum digit sum y. What you can have is by placing all the nines here, right? If I place all the nines, the maximum sum that I will get is 9 into 15, which is 225, around 300, let's say. Maximum around 300 I can go. The addition is correct. That's 180. Okay. So so as you can see, the maximum digits and sum can be up to 100. So y can be up to x plus 300. All right. So the range of y will always be x to x plus 300. So I can just take a direct iteration loop where I can say for y is equals to x, and I will go y is less than is equals to x plus 300 and y plus plus. So it's working in big of 300. Yeah. Example case. Yeah. Okay. So yeah. So as you can see, 9 into 15, it's working like big of 300. You just make every y, find the digit sum of y with the formula, take out the digit sum of this thing, y, and check your y minus digit sum of y is, if it is equals to x, you can just increase the count and return your answer. I guess that's the code. You can do like this. And there are 10 digits of, you can take 10 digits and become 1e9. I am assuming, like, let's say our y is very large number. It has 15 digits, 20 digits. Does it matter to me? No, it doesn't matter to me. Yeah. So your y can be range up to this thing. I can iterate over uh, the whole this thing like x to x plus 300. You can take 200 also, 100 also, whatever is the value is. Okay. Why 15 is 189 is limit? It should be 9. Yeah, you can take up to 81. I'm saying the same thing. Like you can take up to 81. I'm just trying to make you understand that even I take up to 300, it will definitely going to work because there will be a point. I have told you, let's take a maximum y what I can go for. So I just want to make you understand that this work in big of like a constant time for you, big of 81, 9 to 9 or 90 to 10, 90, or take 100 for a much better process. Okay, why this is wrong? NTN, if n modulo 9 is 0, then I just count 10. If n modulo 9 is 0, so if x, and I say 81, it is 0, so then there are 10 digits. For 90, it will break. For 90. Then the answer is 10, but it doesn't check x is really y minus t. Just check what is not actually. Okay, I guess you got your answer in the chats also. So for 90 it will break. Yes, it's failed for any modulo 9. Okay. So I guess you get your answer. So this is the basic approach. If I was doing the problem in the contest, I will do this. I will, and you can take up to 81 also. Okay. Don't like attack on me for this. You can take up to 81, 90, 50. But I'm just taking 300. What's the case of taking up to 300? What matter? Right? Yes. Okay. So I guess this is clear. We can move towards the next problem B. Okay. So in this problem, you are given a permutation P of length n and an array A of length n. We call the permutation P generating for the array A if the array A can be obtained by permutation P by applying some number of operation, possibly 0, of the following types. Choose an index I and perform one of the two replacements. Pi is equals to Pi plus 1 and Pi plus 1 equals to Pi. In other words, in one operation, you can choose two adjacent element of the array and copy the value of one into the other. You're required to report whether the permutation P is generating or not. Okay, so from P, we have to generate A. Right, so for no condition, there are two cases. This is no. So you can copy this. Second one. We're going fee first. Right? Okay. So copy this. This becomes this. So this is same. 2 is not in this array. So or you can just copy this, right? This will come from 1. Okay. So 5 to come to take 5 here. I need to convert 6 into 5 also. Okay. So that's why it's wrong. Same thing here. Mm. If you want to make 4 here, you have to make this thing 4 also, or you cannot like directly this. All right. So you are given with a permutation P1, P2, P3 up to Pn and an array P1 into A3 up to An. They both are same or different? Same. Okay. So you have a permutation P and permutation array A. Now what you can do for any array element like A2, either you can take this value or you can take this value. Okay? Or you can take similar value, and you need to say that can I generate array A from this particular permutation by performing these operations. Pi will be converted into Pi plus 1, or Pi plus 1 will be converted into Pi. So any of these operation I can perform, and can I make the array A or not? Okay, so let's take an example in which my final array looks like this. First of all, you need to note one thing. Wait. First of all, you need to note one thing, that if I am like making this thing, so this is my Pi, right? I can convert my Pi plus 1 from Pi, and from this I can convert this Pi plus 2, and so on. So as you can see, this is a continuous block of elements. And same for this side. If you go, you can just make a continuous block of elements together. You can just read the chats. They have just said that you cannot make for n modulo 9 is failing for some test cases and is equals to 90 or something. So as you can see, these are continuous block of elements. So if you are you have 5 at this 5, if you have 5 in the permutation at some this place, okay, Pi. So you can make continuous number of 5s in both directions, but you cannot make some element 5 while there is a different element in between of them. Okay, so if you find something like this, and it looks like this, it's directly a no. Okay, so it will be a continuous element. So my valid A will always be some continuous number of elements. Okay, so it will always be like this. So if it is continuous number of element, rather than doing this, what I can do, I can just take 4 here. Okay, so let's take this example. Now this is continuous element. I don't need to check for all of these, so I can just say it is 1 and it is 2 and it is 4. So they are made from 1, they are made from 2, they are made from 4, which means my also one more condition is there, that ordering of these elements in the permutation must be same, right? One note, one note. Okay. So the ordering of the elements must be same in the permutation also, because if one is beyond 2, then you cannot take one here. The same logic. So my permutation should be look like some values 1, some values 2, some values 4, and some values. So it should be look like this. Then I can say I can make my array A from this permutation. All right. So I got the approach now. What I have to do? First, from array A, I will check if it is continuous block, continuous blocks of unique elements. Okay. Then the second thing I will do, it's my first part. The second thing I will do, form the new array from A, which contains only unique values. Okay. Which means like if array is this, then I can just convert it into 1, 2, 4. Okay. So this will be my array B. Now from B, check all elements occur in their respective order or not. Okay, so if they occur in respective order of B, then I can say yes, I can make an array A from P. Else you can just return no. So that's all for this problem. I guess it is clear now. Clear? So let's move towards C. People are still focusing on A. Okay, so let's move towards C. So this is problem C. In this problem, Alice and Bob have two integers P and Q, and they are playing a game with these numbers. Yeah, I will explain E1 and E2 for you, E1 and E2, I guess. Div 1, C1 and C2, so they are E1 and E2 pair. They are playing a game with these numbers. The player takes turn with Alice going first on their turn, and a player can do one of the two actions: decrease P by 1 and decrease Q by 1. And we have to do until P is greater than 0 and Q is greater than 1. How will we check the order if it is correct or not? Look, the permutation contains only unique elements 1 to n. So if your array B you make two pointer approach, right? Your array B will point at I and your permutation will be point at J. While your I is not equal to J, increase your J counter. You get your I and J equal, then increase your I counter and J counter also, then keep on going on. Like this you can just do. Right? Right, this is so. Okay. So you can check order in that fashion. Right. Make if you have two arrays B1, B2, B3 and P1, P2, P3, P4, P5. Now your both the pointers are pointing like this. Now check na B1 is equals to I A BI is equals to PJ or not. If they are not equal, do the operation. Increase your pointer, increase your pointer, increase your pointer. You got this value, okay? So it is equals to B1. Then you increase your pointer here, okay? Then the J will be pointing here and go on. If the array, the ith pointer goes beyond this length, then you can say the elements are in the relative order. Okay, that's how you can just do this. Okay, so you can decrease P until P is greater than 0 and you can decrease Q until Q is greater than 1, which means the P will return to 0 and Q will return to 1 at the end. Yeah, game ended P0 and Q1. Bob wins if any point during the game the fraction PQ is equals to in value the fraction 2 by 3 as Alice win. Okay, so given the initial value P and Q, determine the winner of the game. Okay. So this is quite like logical problem, not very implementation heavy or anything like that. You are given P upon Q. Okay, you have to not make this equal. If this is equal, then Bob's win. Okay, so you have to just save Alice from Bob if you want to do this. Okay, so we will discuss D, E1 in 2 also. Okay, so P by Q must not be equals to 2 by 3 if Alice want to win. So in this condition, it is quite difficult to understand. Let's make this cross multiplication. So 3P is equals to 2Q. So this is the condition of Bob winning. Correct? Okay. So Bob can win when 3P is equals to 2Q. Let's say 3P is my X and 2Q is my Y. So if X is Y, then Bob wins. Now tell me one thing. Can I write it as 3P minus 2Q is equals to 0? Correct. So this is a equation of a line. I can say this is an equation of line. And if 3P is equals to 2Q, then Bob wins. But what will happen if your value Y is smaller, which means this Q is smaller? Tell me. It will be beyond this line, where the line will cut. Then the value will be beyond this line. And it will always be possible for Alice to do any operation. Like if P upon Q is there and you want to not make it is equals to 2 equals to 2 by 3, and you know that your P is smaller than Q and it is not equals to 2 by 3. So Alice will decrease this. Okay, then Bob will decrease this. So then Alice will again decrease this. So it will go keep on continuing. Like for any time, any point of time, look, my graph will look like this, where it will meet at point 2 here and meet at point 3 here for y-axis, and x-axis, x-axis. Correct. So I need to reach a point which is here somewhere. So what I will do, if the original P and Q lies here, so it is easily to reach there and not touch this line. Yeah, because this line is where Bob wins. This is my line, and it is where Bob wins. So if I am somewhere below this line, I can say that I can reach the original point, which was P is equals to 0 and Q is equals to 1, where game ends without touching the line easily. Yes or no? Still stuck on A. Yeah. Now, what will happen? Okay, so this is clear. Like if I can say one thing, that if your 3P is equals to 2Q, then Bob wins. Else, if your 3P is less than 2Q, or what will I say? 3P is equals to 3P is this means whatever the value is less than in this line. So I can say the value less than the line. Then Alice wins. Now the thing comes, I will write it this later. But the thing comes, what if value is above this line? Then what will you do? What will happen if value is above this line? So in this condition, there is one case like my Bob winning condition was this. Okay, so if this value is above this line, so this value is positive. Right? If this is positive, then this means 3p is greater than 2q. Correct? Yes or no? I just told you it's one note. Okay, so 3p is greater than pq because it is positive. Now let me just test. Let Alice test. What will happen if I decrease 3p, or if what if I decrease p, or what if I decrease q? Okay, so say I am Alice and I don't want this condition 3p minus 2q becomes 0. Okay, this should not be made. So if I decrease p, it will be like this, minus 2q equals to 0. If I decrease q, then it will be like this. Yes or no? Yes or no? Right? So what I can write this equation, it will be 3p minus 3 minus 2q, and this will be 3p minus 2q plus 2. Okay, so as you can see, this was my original thing. This is my original thing. So when I decrease p, look carefully. So when I decrease p, the value decreases by minus 3, and when I decrease q, the value increased by 2. Okay, so this is what happening right now. So if the value is decreasing by 3 and for q it is increasing, and my 3p minus 2q was positive, so this value was positive, and I don't want to go 0. So from positive to 0, which operation takes us from positive to 0? It's negative operation. So Alice will resist this operation. Okay, so Alice will not do this operation. Yes or no? Okay, so Alice will not perform this operation. Alice will perform this operation. But Bob want to reduce it to 0. So Bob will do this operation. Bob will do this and Alice will do this. So at one point Alice is doing positive operation, and Bob is doing negative operation. So they both will cancel out each other. Okay. So basic name game theory. So if they both cancel each of them, so what will be my average? It will be minus 1. So for in after each 2 rounds, the total value will be decreased by minus 1, which means we are going towards 0. This thing is going towards 0. Okay. So if it is going towards 0, can Alice win? Yes, she can win at 1 point, which means P becomes 0 before your condition 2 by 3 occurs. Okay. So if my P becomes 0 first and the condition 2 by 3 doesn't occur, then I can say like Alice will win at this position. So now I can directly write my code as, if this 3p is equals to 2q, this is the condition for Pop. If my 3p is less than 2q, this is the condition for Alice. Else if, okay, now else there is one condition where if p is less than q, which means p will become 0 first before reaching that state, then Alice win, else your Bob win. So that's was this core idea. of this code. Is this clear? This was the whole code, like this was the whole code C. Is this clear or something which is not? Then I missed the last portion. Oh God. It was confusing during contest. Yeah, it was confusing. Like I was able, I took a lot of time in finding out this third condition. So this was quite complex. You just need to understand, like, take this as like you have sum, which is 3p minus 2q. Okay, and this sum is positive. And after each operation, the average decrement is minus 1. Okay, so the sum will decrease by minus 1, minus 1, minus 1 at each constant. So I can say like I should have enough fuel for P. If I have enough fuel for P, I can write it like this: enough fuel for P such that P by Q becomes 2 by 3. Then I can say Bob will win. But if I don't have enough fuel for P, which means P value is less than Q. Okay, so this is the condition. 1, edge case. No edge case. Why 1, is edge case? Look, if your uh, x will be 3, then y equals to 2. Okay. Uh, maybe. So x is 3 and y is 2. So in this condition, what is happening? Like your x is not equals to y first. First of all, so this is not going to happen. The second thing is also x is less than y. This is not also happening. The third condition is happening where I will check if my original p is equals to q. Yes or no? So original p is less than q, which was 1, 1. So if this is valid, Alice will win. Yeah, wait, 1, 1. What I'm missing here? 3. No, for 1 it will be 3, and for 1 it will be 2. X and Y. Uh, is something wrong what I've written? Like if P is less than Q, then Alice wins, as you have Bob winning in this situation. So if Alice goes first, then she can just convert it into 0, 1 and it will answer. Wait, P and Q 2018. Yes. So is there something I'm missing? Uh, so the condition was okay. Yeah, yeah. Oh, oh yes. Sorry. This was the yeah. Thank you, Violet. So when P is less than Q, Bob wins and else Alice wins. So because if you don't have enough fuel for Alice, then she lost, right? Because if P is smaller than Q, then it will becomes 0 faster. That's why. Yeah, sorry. P is not less than Q. Oh, sorry. Yeah, I just wrote the inverted sign. I thought. Okay. So if P becomes 0 faster, then Bob will win because he will try to get to this line, and if you don't have enough a few for P, then Alice will win. Which means if your P is sorry, if your P is here also, Bob wins, and here Alice wins. So if you make your zero faster, or Q you take down Q below numerator, then it's always true that uh, what I mean that if you have a numerator upon denominator and you make this smaller, so a condition 2 by 3 cannot be occur if P is greater and Q is smaller. So that's why Bob will win. Okay. So yeah, I was sorry for that mistake, but yeah. Okay. So this was the whole idea for this C problem. I guess this is clear, so we can move towards D. If this is clear, we can move towards D. Okay. Uh, yeah. So this is problem D. Okay. In this array, we call a pair of indices ij beautiful if the following condition hold. Okay, so we can look at the D. It's more like a mathematical problem and mathematical brute force problem. So the texts are same, right? So ai into aj should be equal to j minus I. Okay, so we need to count beautiful pairs. In this problem, I just need your help to just let me know. I will ask some questions at each step. Okay. So you are given ai into aj, which will be j minus I. So what? Wait a minute. Maybe. Okay. So just tell me one thing. Do you have control over ai and aj? Do you have control over ai and aj? We cannot do anything about them. Okay. So they can be any number from 1 to I guess 1e6 or 1e7, whatever the value is. 1e9. 1 to 1e9. So they can be any number. We don't have control over them. What we have control is j and I and j. So it is saying j minus I. What is the maximum value of j minus I? Can anyone tell me? What is the maximum value? Take j if it is zero based indexing or one based. Let's say one based indexing, so it will be n and this will be one. So the maximum value is n minus one. Yeah, maximum value will be n minus one. Okay, so maximum value is n minus one. So I can say my ai into aj can be maximum as n, or I can say it will always be less than n. Yes, it will always be less than n. A into aj. True. Is this true? Look, my j minus I can have a maximum value of n minus 1. Correct. So ai multiplied by aj can also have a maximum value of n minus 1. It cannot go beyond n minus 1. Yes, you tell me now. If I take j as the maximum value and I as the minimum most value, I am taking one based indexing, so j will be n and I will be 1. So it is the maximum value that these two pair can achieve in their whole life. Can we go first go through the question once again? Oh, okay. So the question just asked you there are two indices I and j, and you need to count the beautiful pairs. So I and j are beautiful pair if this condition hold. I ai into aj is equals to j minus I. You need to count all the INJs that are possible. Okay, so this was the question. Now, what I was doing is, rather than counting all the pairs of indices because it will go in big of n square, what I can say that ai multiplied by aj is equals to j minus I, and this value can at most achieve the term n minus 1. It cannot go beyond n minus 1. Yes or no? Just tell me. Yes. Okay. So my ai into aj can achieve at most n minus 1. So I can write my ai into aj will always be less than n. This is also true. Like I just transform this thing into this. I can write this also. If I can write this and two, like multiplication of two numbers is less than n. Okay, multiplication of, listen to me carefully. If multiplication of two numbers is less than n, then I have three conditions here. Okay? First of all, one number is root n, another number is root n. So they are greater than equals to root n. Okay, both of the numbers. So this will this equation hold? No. Will this equation hold? If both of the numbers are greater than root n, then it will be multiplied root n by root n, then it will give us n, but my equation says it should be always less than n. Okay. So this condition is false for me if both of them are greater than equals to root n. The second condition that occurs is one is greater than root n, the other one is less than root n. Okay, so this condition can be true. Okay, I'm not sure. This condition can be true. Okay. So similarly, the other condition will also hold, the vice versa thing. The first one is less than root n and the other one is greater than equals to root n. So I can say this can be true also. I'm not sure. I'm not sure currently, but I can say that this can be true. So I have these two equations. Now, first ai is greater than equals to root n and aj is less than root n. The second thing, ai is less than root n and aj is greater than equals to root n. Yes or no? Okay. So what is the maximum value of n? 2e5. Yes, both can be also less than equals to root n, then it's also working. I'm just working on this condition, right? If it is greater than equals to root n, if they both are less than root n, then this will always true, right? Any of them will always true. Just assuming. I'm just assuming. What if they are greater than root n? I have to find for that. Yes, both can be less than root n also. If both of them are less than root n, then what I am going to tell you, the approach that I'm going to tell you, that will work on this also. Okay, this this condition, your fourth condition, it will work on this also by just iterating over these two. So just let me first complete what I want to show you. Look, the maximum value of n is 2e5. So what is the maximum value of root n? 450 something. Yes or no? Yes. Okay. So the root n can be up to 450, something like that. All right. So my equation was ai into aj was equals to j minus I. Let's do for case 1. So this is case 1 and this is case 2. Alright. So let me assume, listen to me carefully. Let me assume AI is less than root n. Alright, AI is less than root n. So let's call this value x. Okay. So my x is less than root n, so I can multiply it with aj, and this will give me j minus I. Can I write equation like this? Okay. So now just take I here on left hand side. I will be equals to j minus x aj. Yes or no? Now I know my x can be up to root n because it is less than root n. AI was less than root n. So my x is also less than root n or equals to root n max. I am taking less than root n. Okay. So can I iterate x up to root n and j up to n? If I can iterate x, if I can iterate j, then I can find a valid I for me. Just affirm me if you are able to get it. What I'm trying to tell you. I can solve this again if you want. If you are not able to understand, and just tell if you are not able to understand. I will just start it again from this one more time. So yeah. So let's start from basics. The once more. Okay. So AI multiplied by aj was equals to j minus I was my equation. Correct. So and we are clear that this value cannot be more than n minus 1. So my AI into aj can be n minus 1 at maximum. Okay. So this is the maximum value that AI minus aj can achieve. Yes or no? Now, if this is the maximum value, then I can write this inequality also. AI into aj is less than root n. Oh, sorry, not less than root n, just root n, less than n, n square root n time constant. Yeah, it works in n square root n. Okay, so your AI into aj is less than n. Now, if both of them are multiplied and it is less than n, then you have four conditions. First is both of them are greater than equals to n, and we will discard this condition. Okay, we will discard this condition because when you multiply two numbers which are greater than the square root, it will always become larger than n, and this will fail our inequality. So let's mark this inequality. This is important for us. The second condition is either of them is less than under root n. So if either of them is less than under root n, I can find a valid index for the other one. Okay, I can brute force on first and I can find the other index I. By brute forcing on j, I can find the other index I. Okay, so let's not go in other conditions. Just think either of them can be less than root n. Okay, so this is my condition. This is my only condition. Think like that. Okay, this is my only condition. So look, I am writing two equations now. AI into aj is less than is equals to j minus I, and AI into aj is equals to j minus I. So these are my original equations. Now just look carefully. I just said either of them is less than root n. So let's take first, in the first equation I am taking AI is less than root n. In the second equation I am taking aj is less than root n. Okay, yes or no? Can I do this? Okay. Yes or no? Just please let me know. So if I am taking AI is less than root n, I'm just marking it. I'm not doing anything like strange. I'm just marking AI as x. Okay. And x is multiplied by aj, which is equals to j minus I. Now I can rewrite this equation. Rewrite, just take one, take I, go here, and take this term and go here. Okay, so just swapping. So it will become I will equals to j minus x a j. This will be your new equation, correct? For the same this equation, it will be ai into x is equals to j minus I. Now pair I items together, so it will be j is equals to I plus x ai. So these are your two equations now. Yes or no? Can I say these are my two equations now? Yeah. So these are my two equations now. Yes. So just tell me. I want to find I for the first. I'm talking about the first equation. I want to find I, which is equals to x minus j minus x is j. I can iterate on j, okay, which will take big O of n time complexity. And I iterate on x also. It will take, let's say, x time complexity. I don't know about this because I'm iterating on x. And what is the maximum value of x? I just tell you that what is x? What is x? X is ai, and what was ai? It is less than root n. Yes or no? Yeah. So I can iterate x up to root n. So this is my total time complexity, n into root n. Yes or no? So I can brute force it. I can brute force it like this for x is equals to 1 to under root n, and for j is equals to 0 to complete n. Can I do brute force it like this? Brute force it like this. If I write this two loops, I can find the index I, which will be equals to j minus x into aj. Because I have j, I have x. I can write my I as like this. I like this. Now, if I can write I like this, can I check if my valid AI exists, which satisfy AI into aj is equals to j minus I. I have AI, I have I have J, I have AJ. Then can't I just check for validity that if this condition satisfied, increase your count? Yes or no? Yes or no? Tell me, guys. Is this not clear? Like this picture which I have made here, is this not clear? You can brute force on like x, which I have derived from the equation. You can brute force on n for j, then you can find your valid I from the equation. And you find your I, you can validate it also after that. You find your I, then validate it. Is your AI is the correct value which you have chosen? Yes or no? By this equation, AI into AJ is equals to J minus I. Yeah, can you do this whole thing? Understood. So if you can do this for first equation, can you do this again for this second equation also? Just do the same thing. Write the same thing. X from 1 to root n. Then you are iterating on I this time. Look. we are iterating on I this time. So I will take I is equals to 0 to n. Now find a valid j which will be equals to I plus x into ai. Now you have aj, now you have j, you have I, you have aj, you have ai. Then validate it again. Ai into aj should be is equals to j minus I. So if this is understood, to quantize it, so we have to do divide by 2 later. No, it won't matter. Like in this equation, you are taking I plus aix. Okay. So yeah, you are telling one thing, right? That if it is counting twice, then rather than doing this operation, you can control it. Like rather than doing this x operation, you can control it by doing a uh, what I have done was a for loop of k is equals to 1 up to k plus plus, and I don't know the stopping point, and I will stop at some point where your condition is already met. I have done this. Okay, you can do this also. Either you can just subtract using the set theory, like this is your set a, set b, you just remove your intersection point. Okay, so the I was trying to understand you the I was telling you the key idea of this problem. Okay, so the key idea is only this, like you can do a n root n operation twice. Okay, which will help you to count or validate the true pairs, which validate the beautiful pairs which are in the form ing, and you can do like do this, and then yes, you can just, if you need to remove count, you can find your operations, like find the intersection operation or store them somewhere, whatever you want to do, like you can do that. Yes or no? But I guess just try it once like this. Okay. Oh, awesome. So the key idea of this problem is only there. Is this clear? The idea is clear. I guess the idea is clear. We can move towards now the last problem of the contest. We will discuss it. E2. There are two problems, but we will discuss it one go. Just directly discuss it for E2. So we can just skip even. Look, square root n won't go beyond limit because you have 1 to 2 second time limit, I guess. Time limit was 2 seconds, right? And there are 2 into 25, and this 2 into 25. Then you do a 450 operation because the square root of n is 450 something, something like 450. So when you do this operation, it multiplies up to 8 into 1e7, something like that. So 9 into 1e7, 9 into 1e7. So something like that. So it is working in under your 2 second time limit easily. So you can just do this operation. You can perform 1e8 operations in one go, right? 1e8 to 1e2e8 something. Yeah. So let's move towards the problem E. Let's discuss E2 directly. Okay. Game over. So this is the hard version of the problem, and the difference between the version in that in easy version you can ask more queries, and n is less. Here n is less than or equal to 30, and you have n plus m queries. Okay, so this is an interactive problem. The jury has thought of a directed acyclic graph, a DAG, without loops and multiple edges. So there are no, which means there are only single edge and there are no loops. Okay, so this means it's some kind of tree which can be connected at some point. Okay, which has n vertices and m edges. Your task is to determine which edge are in this graph. Okay, so we have to determine all the edges in the graph. To do this, you can ask question in the form: what does the kth path look like in the lexicographically sorted list of all the paths in the graph? Okay. So a path in this graph is a sequence of vertices u1, u2, ul, so that I is less than L, and I just go like ui and ui plus 1 in the graph. Your task is to accomplish this by asking no more than n plus m queries. Okay. So uh, listening like this is like a real mess. Just let me explain what the question is asking. So we have a graph which is directed and acyclic. Okay. So there is no cycle. It's like this. Okay. So in this graph, there are also not multiple edges like from one node you don't have multiple edges, so I have drawn multiple edges. You just ignore it. No, it was saying what without multiple edges. Yeah, okay, so there are no multiple edges like this. Sorry. So this is kind of graph you have. Okay, now you are asked one thing that I am not sure about how many edges this have, but I can ask someone a query. Okay, so I say like return the second lexicographically sorted the path, right? So you are asked to where you can return the kth path, okay, which is in lexicographically sorted list of the paths. So if the paths are like 1, 2, 1, 2, 3, then 2, then 2, 3. So as you can see, they are sorted in lexicographically order currently. So if I say return me the second path, so it will return 1, comma 2, okay, a list of 1, comma 2. If I say him to return the fourth path, so it will return a list which is called as 2. So like this, you know, it's working like this. If there are multiple like edges 1, 2, 3, then 1, 2, 3 comes first before 1, 3. Yeah, lexicographically you are aware about it. Right? Yes or no? Is this clear till now? What the problem is asking? So if I ask someone the number, it will return me the that path which is on that number. Okay, so these are sorted in lexicographical order. I have to find all the edges. How can I do this? Any idea? Can someone tell me any idea to solve this? Look, it's it looks tough. It's look like E2. It's not. It's really easy if we discuss one topic. So just I am here. Just tell me that paths look like this in this order: 1, 2, and 5. Correct. And if they are lexicographically sorted, the path 1 to 5 will come before 1, 3. This is true. Now, how many queries I can ask? I have total of n plus m queries, where n is number of nodes and this is m is number of edges. So I cannot ask more than these queries. Correct or no? Okay. So listen to me. Think of this problem as a dictionary of paths. In dictionary, you have all sorted, like you have all the sorted paths. So let's take word from the dictionary. What I can take? Uh, what I can take? App, app. Oh, sorry, apps will come later. Apple, apps, and here come a. Okay, so after that, let's take some other word from starting from E. A, P, P, A, B, C, D, E, F, P, Q, R, S, T, S, A, T. But whatever word is from A starting and comes after, P. Any word, any guesses? And I'm not able to make a word. Happy person. For very easy person. Yeah, you can write the solution in the chat. EQRT. Yeah, let's take EQRT. Okay, so these are my dictionary words. Okay, so they are sorted in lexicographical order. Let me say my path look like A to P, then P to E, A to P, then P, then A to P, then P, A to P again, then L, then E, then A to P, then A to P, then A to S, then A to Q, Q to R, Q to T. Okay, so the paths look like this. Okay, so if I've calculated all the paths for P, if I've calculated all the paths for P, let's take an example. This is one path, this is two path, this is three path, four. So there are four paths for P. Okay. Now, do I have to calculate, like if I know that path of P, count of path of P is 4. So I have A to P, then A to P to E, then A to P to P. Means it will be look like a trie structure, something like this. But not try, like it's not completely a try code. But I'm just trying to explain one thing, that say I this is my path P to P, then A to PP, and P to PP. Then there is a null point. There's a null point, and there is L, and then there is E. So A to PPS, so A to PPS. Then you have A, Q, R, and T. So if you know all the paths of P, which count is 4, count of P is 4. So do I need to traverse again for all the paths? Like if I know, then I don't need to traverse these three things. Yes, I will skip all of them. This will save my number of queries. I can just skip all of them because they are all same. No need to count for A. I can just directly jump to Q. I can directly jump for a path where A to Q exists. Then I can calculate all the path for Q, which will be all the path to R, which will be all the path to T. So isn't this DFS approach? Plus I am doing a counting of previous state. So I got two things. It is a DFS approach, and I am counting previous things. So if it is a DFS approach, I know the algorithm will be DFS, and counting the previous thing, which means I am using a DP state. Okay, DP state of a node, which will tell me the total count of all the paths. Okay, correct. Now I get the count of all the paths. I get the DFS approach. Then my total paths of A, I can write it like this: count of total of path of A will be equals to count of total path of P plus count of total path of Q plus 1. Write it like this. Now This is for this apple example. Okay. Now, what you have to write for code in code, you will say this as your new what I say new count of the q is equals to one plus summation of all the u to v edges count of v. This is u and this is v. So you can write your equation like this. So this will count your all the paths. Yes. Okay. So we know we will doing these two things. Okay. And if we have already discovered like a path from u to v, okay, so we don't need to check for any path which is u to v2x or u to v2y. If I know all the count for this, then you can skip all of them. Yeah, skip these because it will save your queries and it's just redundant operations. You don't need them. Then you can just directly jump to some u to w path. Okay. Then count for this again. Okay, so okay, Anirudh, you are telling me like counting thing, but I have to draw the edges. Yes or no? You have to draw the edges also. Okay, so how will you draw the edges? Can anyone tell me from by counting stuff what I'm doing? Can I draw the edges? Look, when I'm doing a DFS operation, in this DFS operation, I am calling queries. So what queries will do that let's say I gave him find the first path. So it says me the first part is 1 to 2. Okay. So I got to know that there is a edge between 1 and 2. Okay. So I'm not doing that give me second path or give me third path because it might be possible that it will be 2 to 3, right? So it will be a redundant operation. Rather than I will go on DFS operation until I find a path which is 2 to 3. Okay. So if I found a path 2 to 3, I know there is second edge which is 2 to 3. Then I calculate all the paths for 2 to 3. Like say there is a path 2 to 4 also. So I will write 2 to 4 as a path. Correct. Now it might be possible it is a seventh edge or eighth edge. Maybe possible. I am not sure. But why I am skipping all these edges? Again, look, it might be possible the edge structure looks like this. Okay. So if path structure look like this, as you can see, I just called for this, I just called for this, I just called for this. How many call I done? Three. But if I have done a brute force calling by calling all the paths, it have taken me two more redundant operations, which are these. I don't need this because if I count all these paths of two, count the path of two, I got two values, and then I can say that one have three paths. Correct? One have three paths. One, two, and three. Count of two is two. So one has three paths. One, two, three. Now, if one have three paths, I can skip all these three paths. Directly jump to the new index. Got it? Where that's here I was making my DP. Yes or no? Can you repeat what? From where? Which part? Oh, just tell me. Should I start from the code again? Zero? Start from zero or some place where you messed out? Okay, so let's start again once. I hope this time you will able to like clear out your doubts. Look, I have a directed acyclic graph. So the graph will look like something this. Okay, so there's a directed acyclic graph now, and you have a dictionary, okay, which contains all the paths of this graph. So the paths might contain like this: 1 to 2 is a path, 1 to 2. Take this example, right? 2, 3, 4, and 5. So 1 to 2 is a path, 1 to 2 to 4 is a path, 1, 2, 2, 4, and 5 is a path, 1 to 3 is a path, 1, 2, 3 to 5 is a path, then 2 to 4 is a path, 2 to 4 to 5 is a path, then 3 to 5 is a path, 4 to 5 is a path. Okay, so these are all the paths. Yes or no? These are all the paths you have in the graph. Okay, and they are sorted in lexicographical order. If I had any mistake, then please consider me as your little brother. I'm sorry for that. But if these are all your paths, now if I ask you a query that return me the first path, so I get, oh, first path is 1 and 2. So if first path is 1 and 2, I can say that my first query is 1 and 2. Oh, my first edge is 1 and 2. Okay. Now I don't need to check any path which has 2 in it. Yes or no? I will never check a path which has 2 in it. But I will count how many paths does 2 have. How many paths 2 have? Which there are 2 paths to have. Okay. So for all then 2 also. Then if I call for 2 second path, say apart from 2, it will give me 2 to 4. Okay, so I will make my new edge as 2 4. Now I will check for 4. How many paths does 4 have? So 4 have only one path. Okay, so don't check for this. Sorry, don't check for this thing. If you just check for 2 4 and 4 5, then you got to know, like, the path of 4 is 1. You have one path from 4. So you will not check on 2 to 4. You just skip that part. Okay. Then you just say the count of 2 will be 1 plus count of 4, which is 2 paths. And this is true. Yeah. 2 has 2 paths. Okay. So I got my count of 2. And then when you backtrack from DFS, then you get, you will say your count of 1 is 1 plus count of 2. Correct? Currently. So your count of 1 currently will become 1 plus 2, which is 3. Okay, so now if count of 2 becomes 3, then I will say that I will skip this. And yes, why I am skipping this? Because I have already counted these paths. Where? Where I have counted these paths? Look, it is 2 to 4. 2 to 4 is already counted here. It is 2 to 4 to 5. 2 to 4 to 5, and 4 to 5 is already counted here. So I don't need to count these paths already. So I can just save my queries while counting all the edges. Okay. So I for 4 to 5 I forgot to wrote. So I have already counted 3 edges. And how many queries I have done? I have done 3 queries only, which is 1 2 2 4 and 4 5. Okay. Now next query I will do will start from the third index, because I was trending on first. Right? I was currently trending on first, and my new index will comes out to be count of 1, which was 3. So the next index will be 1 3. So I will query 1 3. Okay. So it will say a path from 1 3 exists. Okay. So I got, what do I query? Using DFS. Using DFS. I will show you. I will write the pseudocode. Okay. So don't worry about it. Need to query for 5, right? Yeah. If you query for 5, it will return like 0. Yes or no? It will return 0 because there is no path from 5. For the kth shortest path. Yes, we will query for kth shortest path. So it will always in the sorted manner. Now, if you find how to find the second query, you have to query for kth shortest path, right? How will I find from where I have to go from 1 to then next jump will be 1 3. So the jump, to count the jump, I have to store the total number of paths from 2. Yes, but we don't know 2 to yes, I will tell you how DFS will occur. Then how will it find that the path from 2 to 4 is there. Okay, don't worry about that. Yes, so I am skipping these two things. Okay. Just understand what I am trying to say here, that if you are coming on 1 3, now when you query 1 3, it will say you that 1 2 3 exist, then you write 1 3 exist. Now you will count how many skips you have to done, so you will check for path of 3, and there is a single path of 3, so you will do a skip of 2. Okay, if you do a skip of 2, then you are already checked that 2 is already visited. Okay, so 2 is visited, then 3 is visited, 4 is visited, then you can just skip all of them. Correct. Now, your question, which is right, then how will I find using DFS? How will I find that where I have to go? Correct. That's what your question. So look, I'm writing a pseudocode here. Okay. So the pseudocode will look like, I have a DFS function in which I will call my node. Okay. Then the kth position which I will call. Okay. So it will have one position k, the depth. After that, you can just make a count vector, a visited vector out of these like loop. So you can just directly found. Okay. So this will be your DFS function. I am writing it later. And your main function, what will you do? Your main function, you will iterate on all the elements, all the nodes from 1 to n. Okay. Make a for loop, iterate on all the nodes from 1 to n. If it is not visited, call the DFS. Okay. So here I am calling the DFS from I comma k to n 0. Depth is 0 currently. Okay. Now what will be your initial k? What will be your initial k? It will be starting from the first. Like I will currently start from first path, right? Just tell me what is the first path. Then I will calculate all the paths using DFS. Okay. So k will initially be 1, and then you just do a DFS. After that, your k will be updated because you have to do a jump. Correct. How much k will be updated? It will be updated by count of that particular I node what you are writing. If you are taking it as node, you can write it node here, whatever you want to write. Okay, so I am writing I. So let's take I only. Yeah, quite laggy. So your k will be updated using the jumps. Okay, how many skips you have to do. So my main function will look like this. I don't have to do anything. Make a edges a vector also where you store edges. So I don't care about that currently. Now the main things come. How the DFS will work. DFS will contain your node, your current index where you are standing in the dictionary of all the lexicographically sorted paths, and the depth of each element, which was one has a depth of 1 2 3 4, whatever your depth is, how many DFS you can go, how many depth you can go. Okay, so is this true? Now what we do is first mark we have visited as true, and mark your count of node as 1. Okay, so currently it has 1 value, because we will add here count of this child 1, then count of child 2, right? So it will at the end will become like u2 bh, the count of b, right? Summation of u2 bh count of b. Yeah. So this is clear, like this is not a very like rocket science thing. I'm just starting with 1 because I have to end at the end add 1 in the answer. Okay, for each account. Now we have to find, what do you have to find? We have to find the path. Okay, so let's assume my current index is k plus 1. Okay, I've called for k, then my next immediate function will be k plus 1. Okay, So now you have to calculate all the paths. Okay, so you have to go on DFS thing. So while it is true, yeah, I made an infinite loop while true. Okay, and in this infinite loop, what I will do, I will query my paths. Okay, so how will I query? I will just make a path vector where I will just query of k, index, sorry, query of index. I'm made an index, query index. So it will return me a path vector. I got this path vector. If it is empty, if my path vector is empty, then I can just break out, because it means that I have reached the leaf node. I'm going like this now, 2, then 3, then 4. Oh, I got a leaf node, and there is no path from here. So this I can say it is uh, it is returning 0. That's why it is returning 0, and the path vector is empty. So I will break out from here. Correct? Is this clear? Now, now listen to me carefully. Now here it is starts where I am checking how many jumps I have to make. Look, what if your path dot size, your path vector size, is less than equals to d plus 1, depth plus 1? What does this signify? And what I have to do in this situation? Just tell me. If my depth is greater of that particular node, then the size of the list which are returning, the path, the size of the path which I am getting. So this means the path which is returned is has uh, has depth not is equals to the original node. So what I made the original node, it is named as node correctly. So, so it was not equals to the original node. So the current path is not the path of u or node. Okay, so I can say the current path is not the path of the node which I am currently standing on. Okay, so the path which I have returned from the query is the wrong path. I don't have to use this path. Okay, so or I can say that we have moved to some different edge of the graph. Okay, so we have moved to some different edge of the graph which is not valid for us. Okay, so that's what this means. So I will break out from here also. This is wrong. Correct? Is this clear till now? Yes. One confusing. Oh, look. Just try to imagine it like this. You are standing on path one here. You're standing on path one here. Okay. Then you are going. You are checking. Okay. So this is the path. This is the path. And out of the sudden, that you should get this path, right? 1, 2, 3. But you are getting a path which is as a size 2. And can you say that you are standing on one current node 1? No, you cannot say that you are standing on current node 1. It might be possible you have diverted from your path. Okay, the problem is that there is a compiler code which is running on backend, interactor code. Okay, so that interactor, I have to interact with that, and I will just query it, and he will say that this is the path. So I cannot just guess it what is the tree. I can just assume it using the universal truths, which is that if I'm standing on this node and it has a depth of d, then the path I get must also have a depth of d or equals to d. Okay, so this means that if I'm standing here, this is my current node, and I'm going using a DFS, and so the depth is 4. Currently, the depth is 4 for this tree. Okay, but if I get a path which is of length 3, so this is contradictory, right? How can I get a path of length 3? And if I'm standing, if my like depth is 4, so which means if I might be in some different edge or different branch of that tree. Maybe it is possible like I have ended here. It, it might be possible I have ended here, or I might go somewhere here. So I might have entered some different branch. Okay, so I that's why it can be 1 2 3 4. Yeah, it can be 1 2 3 4, but I get 1 2 3. Yeah, so you have entered some different. No, if you are getting 1 2 3 4, you will get 1 2 3 before 1 2 3 4. Yeah, because in lexicographically sorted order, 1 2 3 comes before 1 2 3 4. Okay, so you will get this first. So after this, your D will increase, depth will increase, and you will get this thing. So your depth will equal to. But this is true. Like if you are, if I say that, uh, let me explain. If I say that you are standing on 1 2 3 4, you have a depth of 4, then you suddenly get a thing which is 1 to 5. In 1 to 5, you can see that depth is not is equals to like the size is not equals to the depth, which means I have diverted from my current DFS path. Correct. And if this is true, I can also not say that I am standing on one. It might be possible I am standing on some other value. Yeah. It might be possible that I am standing on some other value which was diverted from that. Okay, correct. So if this is true, after that, what I can do, I can take a if this is to break out from the loop. Other than you can just take out your V edge, which will be the path of depth plus one, which is the latest edge you have added. Then you can push your edges node comma V. Push this into your edges. So you got one edge. Now, if you have pushed this, now what you have to do? If you have not visited the basic DFS, if not visited V, then call DFS of V, comma your current. Uh, what was the K? You have taken K was IDX, right? IDX, the new IDX, and your depth will be increased by one. Okay, so your DFS will be called. Uh, Now, if your DFS will be called after that, what you have to do? You have to add your count. This is equals to count of V. Increase your jumps. When you increase your jumps, also increase your index also. Then index plus is equals to count of V. So that's all. This is all the DFS you have to do. Is this clear? Okay, wiring during this question. This one. Adding on to the last example. If we query 3, you have 23, query 4, 23, 5. No, this you don't understood. Look what I've done. When you're querying an index, you call your current index as k plus 1. Okay, your current standing index is k plus 1. Okay, so you query that index. Okay, after querying that index, you will get some value. You will get a path. Say you got 1 to 2. So you got this path. Okay, and this is equals to your. It is greater than your depth. So you will say your current depth was 1, and it is greater than depth. Okay, so it is a valid path. If it is a valid path, there is an edge between 1 and 2. And if it is an edge between 1 and 2, I can store the edge first. Okay. Just to get at it, how increasing k, we get the part where we are adding count child plus 1. We're querying during DFS. Okay, so for each k, look, k is my index where I'm standing on the vector of that, or what to say, dictionary of those, all the paths where paths are stored in the lexicographically sorted order. We are querying the index where currently I'm standing on. Currently I'm standing on 1. I queried that index. Okay. And if I get 1 to 2, I will say that path from 1 to 2 exists. Okay. Now, just don't think about this first. Here, look here. I will get the node B as the latest node which I have added into my path, which is D plus 1. Then I can update my edge. Okay, this is clear. These two things are clear, like what we have done. And this is also clear. The visit, if it is not visited, you just do a DFS, the basic standard DFS. Okay, what we do if not visited, that's DFS. Now this thing is nothing. I have count U as one, and for each like count V, which is U has a child V. So I will add these count so that I can maintain my skips. And how I'm maintaining my skips? I am increasing my index here. Look, I am increasing my index. That's equals to count of V. So you are saying the right thing that for the first time I will do this. Okay, for the first instance I will do this. But after all these instances, I will have secured a path from 2 to 3 or 2 to 4. Okay, so I will then skip all the paths which consist of like 1 to 2 to 3 to 4. Then I can skip these paths, right? First, I have increased my index plus equals to count of L. Currently, I am just going one by one, one by one. Then after that, my skips will be registered in the index. Hmm. Can I take one example to tell you? Look, say, okay, so this is your say directed acyclic graph, which we don't know about. Just write all the paths in here. The path 1 to 2, and 1 to 3, 3, 1 to 2 to 4, 1 to 3, 2, 2 to 4, 3. Ah, yeah, this diagram. Please help me in the diagram also. Okay. So you have a path 1 currently. So 1 to 2, then 1 to 2 to 3. Then you got 1 to 3 as a path. Then you got 2 as a path. 2 to 4 as a path. 3 as a path. And 4 as a path. Okay. So these are all your paths in lexicographically sorted out. Currently you are standing here. So you won't call this. Obviously you won't call this. You will call the k plus 1. Okay. 2, 3 is left. Okay. So yeah. So 2 to 3 path here. Okay. So my k was currently here. Let's go code by code. Okay. Here. What I am doing before calling DFS, my k was 1. Then my 1 was not visited, and I called DFS of I 1 comma k. Okay. So 1 is not visited. So I called this DFS of 1 comma 1 comma 0. Okay. So depth is currently 0 and it is 1. So I will query in my DFS what I was doing. Look here. I was first marking visited node as 2 and count node as 1. Okay. Let's make two array. This is my visited array and one more array which is my count array. Okay. So mark this as 2 and count as 1. Okay. Now before querying, I have updated my k. My current index is k plus 1. So my current index will become 2. Okay. Now I will query 2. What is my 2? So this was your query 2. Okay. So this is index 1. This is index 2. This is index 3, 4, 5, 6, 7, 8, and 9. Okay. So they are 9. So I have queried 2. So 1, 2 will return as a vector. So I got a vector 1, comma 2. Okay. So depth was currently 0, correct? And the length of array is greater than d plus 1. Length of array is greater than d plus 1. Okay. So this is a valid path. If this is a valid path, what is the recent index which I have added? It is 2, d plus 1. Oh, so I can just say 0 plus 1 is 1. So this is the recent index which I have added. Okay. So my edges will contain the node 1 and the edge 2, okay, the recent one. So 1 comma 2 is my edge. Okay, so this is okay. Now, before adding my index, I will call my DFS because 2 is not visited. I will call my DFS on 2 comma your current index, which was 2, and your what was this, depth was 1, depth was increased by 1. So now you call this. Then when you call this, you will again do the same thing, mark true as 2, and your current 2 will have a count of 1. Okay, now you query the third index because you have k is equals to 2. You will query the third index. Okay, so third index says 1 2 2 2 3. So I got 1 2 3. Now which is the latest node which I have added in the path? It is 3. It is 3. Yeah, and the node is 2. So I will add one edge 2 and 3 in my answer. And after adding this edge 2 and 3, I will call a DFS over 3 because 3 is not visited. Let's call DFS for 3 with current index 3 and depth is 2. Okay. So when you call this, it will first again do the same thing, mark visited as 2 and count of 3 as 1. Now when you are called this, you will ask for the fourth query. Okay, you will ask for the fourth query. Now look what I meant to say. Okay, you called the fourth query and fourth query returned 1 3 1 3, and your depth was 2. Is this size 2 greater than 3? No, this is an invalid strategy, or I can say invalid condition, because I have diverted from the path 1 2 2 2 3. I was going in this direction and then suddenly I got a path 1 3. So it is wrong. Yeah, so we broke off from the path 1 2 3. So if we got wrong, we just break out from the loop. Okay, so there was a while loop going on, right? Infinite while loop. So if we break out from this loop, what will happen? Look, what I was saying. I will I had where I was we yeah. So this thing is false. Now I break out from the loop. I break out from the loop. Neither this appended, neither this appended. Okay. So DFS will return. Okay. We will backtrack to this thing. Now when we are standing on this stack space, or what we say is that, or this is recursive stack. Okay. We are standing here. Okay. And what we have done till now, we have visited this. So now I will update my count of 2 with count of v. Okay, so count of 3 was 1. Okay, so count of 2 will be updated with 2 because they both will be added. Okay, so they have been added. Now they have been added. My index will also get updated. My current index here was 2, and then 2 will be increased by 1. Okay, so 2 will be increased by 1. I got a index new index 3. Okay. What index I had? I guess I had index 3 already. I've called the index here 3. Oh yeah, I called the index 3. So it will become 4. Index will become 4. Sorry. I've called the index 3, so it will become 4. Now I have made the fourth index, P2. So I have made the fourth index. So I will, after that, while loop will go again because while 2 is going on, infinite loop is going on. So I will come back into this loop and I will query the fourth path. Okay. So this time the fourth path will come out to be 1, 3. Now, if you look, it is still not greater than 2. If it is still not greater than 2, which means I am not currently standing on path of from 2. So I will break out from here again. Okay. So when you break out, you will go back to the DFS of 1. Okay. So we will go back to DFS of 1 here. Now, when you go here, you will update your count and index. So your count will be increased by 3 and your current index at that time was 2. So it will be updated by 2 plus 2, which will become 4. Look, I am currently iterating on the same index. I am trying to find 1, 3 exists to which element. Okay. So when you are standing on 1, 3, then if you are standing on 1, 3, what will you do? You will query again, like you will query 4 again, and you will get 1, 3. Now at this point, 2 is greater than 1. Okay. Now this is your valid path. Now you are currently on DFS of 1. This is your valid path. And if it is valid path, you will check. You will first add your path in the edges. 1, 2, 3 is a path. As you can see in the diagram, there was the diagram. I just forgot the diagram. Yeah, there is the diagram. As you can see, look, 1, 3 has a path, and 1, 2 has a path, and 2, 3 has a path. I have already visited these paths. Okay, so I have already visited these paths. So if 3 is visited, 3 is already visited, I will not do a DFS again. Okay, then I will try to find the next path in this operation. Okay, I guess for 2 I just forgot to do this fourth path. I'm not I'm reiterating, so I just might have forgot iterating again because of while loop. So you just I have forgot this path. You can just add this path also. 1 to 4 will come. Add one index. Yeah, I have sorry, I just forgot to write 1 to 4 here. But I hope you are able to understand that 4 was not there. I hope. If 4 was not there, this is condition is true. This condition is true. And as you have seen, I have iterated only 3 times, or 3 plus 3 times. Okay. So I have iterated only 3 plus 3 times. And rest of these paths have not been discovered. And they don't need to be discovered again. Your DFS will break out in big of n plus m iterations only. Okay. So you will make all this array. You will store these because it will help you to tell how many skips you have to do to find the next path. Okay. So this was the whole approach. I hope you are not now able to understand. You can dry run on your own and you can get a very clear idea like what is happening during the thing. So that one is the root. But yeah, we can assume one is the root node. Doesn't matter. Like one is the root node because if it is sorted in lexicographical order, my paths will always be sorted in lexicographical order. So if one contains a path, like if there's a path from 1 to x, it will always on the top. Yeah, yeah, one emerges for as the shortest path. If one don't contain as a path, let's say one is not a root node, there are multiple edges coming to one. So it might be possible 2 has a path or 3 has a path. So they will come on the top always. So that's the case. And for that you are doing right a for loop from 1 to n and checking if your it is not visited, then you do a DFS at that time. So this was the key idea, right? So this was the idea of this problem. I hope you were able to understand. Only 5 people are watching now. Okay. So let's wrap up this post-contest discussion. Thank you for joining, guys. I hope you were able to. If you are made till here, then I hope you will able to solve up to E2 now. And thank you. We will meet again really soon. Yeah, it's this ID. And no, I'm not SD2. I'm just a college student right now. Okay. So please check out the Instagram channel also. We have a lot of things there also, and you can just go on Repobif platform also, check out the new see roadmaps we have made. And as we have mentioned, Premier Route to registration has started. You can start registering in that also. And thank you for watching. We'll meet again in the next post contest discussion. I hope you enjoyed and have a good day or good night, whatever it is in your time. Thank you for watching. Bye bye.